These massive structures of steel and concrete seem like they could stand forever. But what happens when they need to come down? How do you dismantle something that massive, especially when it's squeezed between other buildings in a bustling city? It's not as simple as swinging a wrecking ball. Welcome to the incredible world of building demolition, a field where engineering, precision, and raw power come together in a spectacular dance. Today, we're going to pull back the curtain on the science and strategy used to bring down the tallest and heaviest buildings safely and efficiently. From towering cranes that munch on concrete hundreds of feet in the air to the explosive precision of controlled implosions, the methods are as fascinating as the buildings themselves. So, stick around as we explore the tools, the techniques, and the sheer brainpower required to level a giant. First, let's talk about the most common method for shorter buildings, which is often the starting point for taller ones too: mechanical demolition. This is the hands-on piece-by-piece approach. Imagine giant metal dinosaurs chewing away at a building. That's not far from the truth. We're talking about high-reach excavators, which are basically massive arms that can stretch over 200 feet into the air. At the end of these arms you'll find different attachments depending on the job. There are powerful hydraulic shears, often called crackers or crunchers, that can slice through steel beams and reinforced concrete like a pair of giant scissors. Then there are pulverizers, which are designed to crush concrete into smaller, manageable rubble, separating it from the steel rebar inside. The process is methodical. Demolition crews start from the top and work their way down, floor by floor. This top-down approach ensures the building's stability is maintained for as long as possible, preventing any uncontrolled collapse. It's slow, it's dusty, and it requires incredible skill from the machine operators, who are essentially performing surgery on a colossal scale. They have to carefully plan each cut and each bite to guide the debris exactly where they want it to fall, usually into the building's own footprint. This method is favored in dense urban areas because it offers a high degree of control and minimizes the impact on neighboring structures. But what if you need to take down a truly massive structure like a 40-story skyscraper or a huge, sprawling stadium? Mechanical demolition could take months or even years. That's when engineers turn to the most dramatic and awe-inspiring technique: controlled implosion. Now, the word implosion is a little misleading. The building doesn't actually collapse inward on itself due to a vacuum. Instead, it's a carefully engineered, gravity-assisted collapse. The goal is to use strategically placed explosives to remove key structural supports, causing the building to fall in a predetermined path, typically straight down into its own footprint. This is where the real genius of demolition engineering shines. Before a single explosive is placed, a team of engineers studies the building's blueprints for weeks. They analyze the structural skeleton, the columns, beams, and support walls that hold everything up. They identify the critical load-bearing points. The plan is to weaken the structure just enough for gravity to do the rest of the work. It's like pulling the right Jenga block at the perfect moment. The explosives used are highly specialized cutting charges. For steel columns, linear-shaped charges are used. These charges focus the explosive energy into a thin, jet-like line that can slice through thick steel in a millisecond. For concrete columns, a technique called drilling and blasting is used. Holes are drilled into the concrete supports and packed with explosives like dynamite or gelatin. The placement and timing of these explosives are everything. Charges are placed on several lower floors of the building, not just the ground floor. This is to create a crumple zone that helps absorb the energy of the fall. The real magic is in the timing. The detonations are sequenced with millisecond delays using a device called a blasting machine. The sequence usually starts at the center of the building and moves outward. First, the charges on the core columns are detonated. This causes the center of the building to start falling first, pulling the rest of the structure inward as it collapses. Then, fractions of a second later, the outer columns are blasted. This inward pull is what gives the impression of an implosion and is crucial for containing the debris field. The entire explosive sequence, from the first blast to the last, might only last a few seconds. For those few seconds, a building that stood for decades is transformed into a falling cascade of concrete and steel, guided by physics and meticulous planning. Before the big day, the building is prepped extensively. Non-structural elements like walls and windows are removed, and a protective fabric, like a chain-link fence covered with geotextile cloth, is often wrapped around the blast floors. This blast curtain helps contain flying debris and reduces the dust cloud. The area is completely evacuated, and the moment of detonation is a breathtaking spectacle of controlled destruction. But explosives aren't the only chemical tools in the demolition arsenal. In some situations, a slower, quieter method is needed. This is where non-explosive demolition agents come into play. These are also known as expansive mortar or soundless cracking agents. Imagine a chemical that can do the work of dynamite but without the bang, the vibration, or the flying debris. How does it work? It's a powder that you mix with water to create a slurry. This slurry is then poured into a series of holes drilled into the concrete or rock that needs to be broken. Over the next few hours, a chemical reaction takes place. The slurry begins to expand with immense force, exerting a pressure of over 20,000 pounds per square inch. This slow, steady pressure is more than enough to crack even the most heavily reinforced concrete from the inside out. The pattern of the drilled holes determines how the concrete will fracture, allowing crews to break it into smaller, manageable pieces for easy removal. This method is perfect for sensitive environments, like demolishing a bridge pier right next to a historic building or working inside a hospital where noise and vibrations are strictly forbidden. It's the silent giant of the demolition world, powerful but discreet. It doesn't have the drama of an implosion, but it offers a level of precision and safety that is unmatched for certain jobs. So, we have the mechanical giants and the chemical powerhouses, but how do you choose the right method? The decision is a complex puzzle involving many factors. The first is the building's structure. Is it a steel-framed skyscraper, a reinforced concrete monolith, or a brick-and-mortar structure? Each material behaves differently and requires a specific approach. The second major factor is the surroundings. Is the building isolated in an open field, or is it sandwiched between other occupied buildings? In a dense city, the risk of damage to adjacent properties, underground utilities, and public infrastructure is the #1 concern. This often rules out a full-scale implosion in favor of a more controlled, top-down mechanical demolition. Cost and timeline are also huge considerations. An implosion is incredibly fast on demolition day, but requires months of expensive preparation. Mechanical demolition is slower but can sometimes be more cost-effective overall, especially since it allows for better sorting of materials for recycling. Speaking of which, recycling is now a massive part of the demolition industry. In the past, demolished buildings just became landfill. Today, up to 90% of a building can be recycled. Concrete is crushed and used as aggregate for new construction projects or roadbeds. Steel is melted down and reused. Wood, glass, and other materials are all sorted and given a new life. This focus on sustainability has transformed demolition from a purely destructive process into an act of deconstruction, the first step in a new cycle of building. Let's recap the entire journey. It starts with an intense planning phase where engineers become detectives, poring over blueprints and conducting site surveys. They decide on the best strategy: the patient, top-down munching of high-reach excavators, the silent but immense power of expansive mortar, or the dramatic, gravity-defying spectacle of a controlled implosion. If it's a mechanical demolition, skilled operators in their giant machines carefully dismantle the structure floor by floor, like peeling an onion from the top. If it's an implosion, the building is prepped like a patient for surgery. Key columns are fitted with precisely engineered explosive charges, all wired together in a sequence timed to the millisecond. On demolition day, with the area cleared and safety checks complete, a button is pushed. In a matter of seconds, the carefully placed charges sever the building's legs, and gravity, the ultimate demolition tool, takes over. The skyscraper folds neatly into its own footprint, a testament to the power of engineering. The dust cloud, a mix of concrete and history, is the final punctuation mark. After the dust settles, the work is far from over. A new army of machines moves in to sort the rubble, separating steel from concrete, preparing tons of material for its next chapter in the world of construction. So, the next time you see an empty lot where a giant once stood, you'll know it wasn't just brute force that brought it down. It was a symphony of science, planning, and incredible skill. The art of unbuilding is just as complex and fascinating as the art of building. Thanks for watching. If you found this journey into the world of demolition as cool as I did, hit that like button and subscribe for more deep dives into the amazing world of engineering. See you next time.